This formula is called as exponentially weighted moving average. This formula helps us understand pattern by looking at previous steps. So if you take a stock market, stock price generally depends on previous day's stock price, right? Previous maybe 10 days or 20 days stock price. So you can understand that pattern. So here, in this formula there is beta. The beta is a hyperparameter which makes the line move in different directions, right? This red line is 1 beta, right? Beta is equal to 0.9 actually gave us the red line. Beta is equal to 0.1 gave us the green line. So if you look at this formula, v of xt, right, at a time step t, x at a time step t, right, x at a time step t is dependent on v of x t minus 1 plus 1 minus beta into yt, right? At that point, what is the actual y value? Right? This is the predicted value. This is the actual value. So we are actually trying to understand the pattern, the recognition, the relationship between the predicted value and the actual value. V of xt is the predicted value. Yt is the actual value. So we are trying to understand, or we are trying to manipulate this beta and then try to create a correlation between this function and this yt. That is exponentially weighted moving average. We call this as exponentially weighted moving average because we are taking the previous steps into consideration. Okay, if I take beta is equal to 0.9, the equation is going to be like this. V of x1, right? First time steps predicted value we are trying to find, our relationship between the actual y1 and the predicted one we are trying to see. Right, so 0.9 into v of x0, v of x0 is 0. Okay, so I substituted that here, and then 1 minus beta into y1. Right, so v of x1 is equal to 10% of y1. Is that equal? V of x1 is that equal to y? V of x1 is that equal to y? Yes, no. Getting it? Yes or no? I tried to use this formula and substitute beta is equal to 0.9 and tried to predict v of x1, which actually came as 10% of y1. On that day, whatever the stock price market, whatever the stock price, when we used this formula to calculate, we have got 10% of that price. Is that correct? Is that correct prediction or wrong prediction? Getting it or not? Guys, you are all silent. I cannot hear you, I think.
We got it, sir, but here your question is, we are not understand your question.
Okay, okay. See, suppose that this is a function, right?
Yes.
And you are trying to predict a particular day's stock price.
Yes, sir. Yes, sir.
Okay, when I used that function, I got as 0.1 of that stock price.
Yes.
Today's stock price, right? Whatever today's stock price, I already know. But I wanted to use this formula and trying to find that stock price. But I got as today's stock price 10% is the prediction of today's stock price. Is that prediction correct? That's what I'm asking. Is the function calculating it correctly? Still not understood.
No, if the function calculates it correctly, we should get exactly y1.
Y1, but 0.1 y1 it is getting, right? So that is the point I wanted to explain. So V of x1 is not calculating correctly. Maybe because beta is wrong, right? If you change beta to 0, what will happen? You substitute beta here, this is 0, right? Vx0 is anyway 0, right? This is going to be 0. 1 minus 0 into y1, y1. V of x1 is equal to y1, right? So beta 0 is satisfying, but beta 0.9 is not satisfying. But you know, if you see, right, if you calculate V of x2, right, then you will see a little more improvement in the formula. When beta is equal to 0.9, there will be a little more improvement. If you see this here, I substituted 0.9 here, right? V of x1 I used here. And what is V of x1? 0.1 into y1. So I substituted that here, right? 0.9 into V of x1 plus 0.1 into y2. So again we are taking 10% of that day's stock price, and then a little bit of 9% of 9% of the yesterday. Okay, if you look at V3, right, here it is 0.9 into Vx2 plus 1 minus 0.9 into y3. So Vx2 we already know this part, right? So we substituted that here. And then 0.1, 10% of today's price I'm taking, but to calculate the rest of the value I'm using the previous prices. See this 10% of today, 9% of yesterday, 0.8% of y1. And if you calculate like that, right, maybe at one point in time, maybe at 10th we are more, you will get a formula that will actually be equal to yt. V of xt is going to be equal to yt after 10th iteration or so. Got it? The point here is beta 0 will help, but there is no understanding added of the previous steps, right? But when beta is equal to 0.9, we're adding previous steps understanding or previous steps y values to calculate current value. Got it? V of xt is calculated using all the cumulative sum of the previous steps and the current step. Got it?
Yes,
Yes,
sir.
sir.
Right? So this is the point you need to understand. So here, why are we understanding this? Let us understand that first and then move on to understanding more of it. So if you look at momentum is one optimization function. We have seen SGD, right? Stochastic gradient descent as one optimization function. What is the formula to calculate next gradient value, next W? In stochastic gradient descent, what is the formula to calculate next W?
Previous
W
W minus alpha into
Ah,
derivative of the slope.
cost function with respect to W, right? But if you see here in momentum, we have used V of, right? So W is equal to W minus alpha into V of dj by dW we used. B is equal to mu minus alpha into V of. So in stochastic gradient descent, it is just dj by dW, but in momentum, it is V of some function of the derivative. Okay. This function is nothing but exponentially weighted moving average. So every time you try to calculate the gradient, you actually consider the previous gradients. What is the advantage of doing that? The next gradient calculated is going to be more accurate, right? We know that in a gradient descent algorithm, the convex curve is not going to be smooth, right? In stochastic gradient descent, I think I'll open video. Right, in stochastic gradient descent, see this, it is not smooth, right? We know that. So we, instead of making one step, if you understand the pattern, you can actually jump from here to here, here to here, here to here. Like, instead of conventionally moving, you are actually making jumps. How are you understanding that jump? By using this formula, V of dj by dw. Every iteration you calculate dj by dw. At time step t, you know dj by dw. You know y value. Okay, you know y value at time step t, or time step I, you know the y value. You are using that y value, and you are using the previous values and trying to calculate the dj by dw value, and use that to calculate the next w. That way, the movement is going to be faster, the convergence is going to be faster. SGD is good, but we are trying to make it better by using exponentially weighted moving average formula. That's that's where we are actually trying to understand, calculating xt times value, we are using all the previous y's. Got it? Did you understood the importance of understanding exponentially weighted moving average? Any questions there? Yes, no? Any questions, Andy?
No, sir. Yes, sir.
Okay. So, that's the use. And this is actually time series formula. Okay. Exponentially weighted moving average is a time series formula. Time series means t time steps value can be predicted using t by all previous steps. Maybe they are 10, maybe 5, maybe 20. We don't know, right? So you can use n number of previous steps and predict previous steps values and predict current value. Or current value is dependent on n previous steps, whatever. So RNN is a better neural network to do time series problems. So we'll see that. Okay, but this is a mathematical formula to understand patterns in a time series. So we'll have that kind of a pattern, gradient descent also. If you know the pattern, you can use the formula to calculate next gradient very efficiently. That way the theta movement will be faster. We are trying to improve SGD optimizer. Okay. So here, there is a formula 1 by 1 minus beta days. When you actually take beta some number, it will actually considered, the previous this many day steps. I have considered 0.9, beta is equal to 0.9. If you substitute here, 1 by 1.0.1 is going to be 10 days. If you take 0.1, it's going to be 1.1 day only, previous 1.1 day only. Yesterday I clearly showed, how it is. Actually Seshiram asked and I clearly showed. If you want, just drag through it and try to look at it. Maybe at the end you will have it, right? So if the beta value is small, the consideration is going to be, very low. If you take beta is equal to 0, it's going to be that day only. No previous days is considered. Okay, are considered. So that is exponentially weighted moving average, and in momentum, the exponentially weighted moving average is the formula we use to calculate the next gradient, and we used that as the value to convert, or actually converge towards global minimum. Okay, so that is momentum, and RMS prop is a little more advancement, right? So these are all mathematical tricks. That's it. Okay. So S of dj by dw is equal to B of dj by dw plus 1 minus B into dj by dw whole square. So better pattern, right? This one is understanding something, but RMS prop is going to do a better pattern. Really small number compared to. So dj by dw is small compared to dj by db. Okay, when we use below formula to update weights, gradient. Yeah. So if you look at the gradient movement, right? This is vertical direction movement. So this is called as contour plot. Did I explain what is contour plot? Did I explain contour plot?
No, sir. I think.
No. Okay. Let me. So it is simple only, right? You will have that mentioned in some of the articles. Understanding contour plot is important. Just simple concept. It's 2 minutes concept. Generally, this gradient descent curve is going to be convex, right? screenshot. So generally this gradient descent curve is going to be like this, right? Like that. Okay. Suppose that this is theta and this is x, sorry, j of x cos j of theta, right? And if there is theta 1 and theta 2, suppose that there is theta 1 and there is theta 2 also, right? Then what happens? This becomes a bowl, right? This becomes, I don't know how to draw a bowl. 3D. I think I drew it well. Okay. So this becomes a bowl. Okay. There is a third dimension, right? So it becomes a bowl. So if you want to represent a bowl and a two-dimensional plot, what you should do is cut it here, cut it here, cut it here. So if you cut the bowl, right, maybe like that, slice it there, slice it like that, slice it like that, slice it like that. You will get rings, right? Will you get rings, ring, right? Like this, the ring you will get, right?
Yes, sir.
Those rings are the contour plot. Okay, those rings are these contour plots. This is the top ring, this is the first ring, this is second ring, and this is third ring. Okay, so when I say ring, right, on this ring, cast is same. See this, I cut here, I cut here, I cut here, I cut here. On this ring, cast is same. I actually converted this three-dimensional plot into two-dimensional plot, right? So this is theta 1, this is theta 2. Suppose that I cut it on the cast, right? So for a set of thetas, the cast is same. For a set of thetas, the cast is same. On this ring, the cast is same. On this ring, the cast is same. On this ring, the cast is same. Even though thetas are changing, the cast stayed the same. Okay. So that is the contour plot. This three-dimensional plot only we represented in 2 dimensions, right? By cutting it at a certain cos. Okay. So here there is a when theta is moving, right? It actually starts moving somewhere here and then starts moving. There will be theta 1 and theta 2. There will be two thetas actually moving, right? So they'll actually move slowly here, go back, go forward, backward, forward, backward, like that. It will move, and here also it will jump around. I think I should have taken another color. Right? It will start somewhere here, and then it will actually move around like that. Move around, and then here also it will actually move around, right? So there is a vertical movement and there is horizontal movement, right? So this is vertical movement, right? In theta 2 direction it is vertical. In theta 1 direction it is horizontal. Okay. So if you think the B is a theta 0 and this is theta 1, right? That is what the theory is talking about, vertical and horizontal. So B is vertical and theta 1 is horizontal, or either way you can take. Okay. So it is moving in 2 directions, right? We should actually reduce this oscillation. The vertical oscillation, if you reduce, right, the movement is going to be faster. Horizontal oscillation should be more compared to vertical oscillation. So to know this RMS prop, right, it will try to reduce vertical movement. Okay, the gradient movement in vertical direction is less and horizontal will be more. I think I spoke it result, but result is resulting in, yeah, I think the same thing. I know when you actually use RMS prop, it is going to move it faster by reducing the vertical movement. This formula actually helps reduce that. There is a lot of theory and math behind it, but you conceptually try to understand. Basically, this is exponentially weighted moving average only. But additional thing, right, is a square root. Got it? Keshwa, mute. Right, got it, right? So while calculating this, we were actually using dj by dw only in gradient descent, stochastic gradient descent or gradient descent. But here you see it's a bit more complex formula. Dj by dw, this is the original gradient divided by np square, right? Np square of s, whatever we calculated here, we are taking that and squaring it plus epsilon. We are adding epsilon because this is on the denominator. Sometimes we may get this value 0. To avoid by divide by 0, we are adding this epsilon. Epsilon is generally 10 to the power minus 8 or something. In the equation, in the API, right, you will have this mention of this epsilon and all these terms. Okay. So for momentum, the beta is called as B1, beta 1. For RMS prop, the beta is called as B2. And in Adam, right, we'll use both formulas. We are calculating momentum, we are calculating RMS prop, we are using both in the formula. W is equal to W minus alpha into, see, this is the momentum formula. This is RMS prop formula. Root mean square propagation, we call it as. Okay. So these are all mathematical manipulations to understand pattern and how the theta is actually moving, from here to here, here to here. Again, this will also move, right? So both thetas will move. If you have 10 thetas will move simultaneously, right? That whole thing can be controlled or understood, and the jump can be made faster by using these formulas. Okay, so these are the advanced optimization functions. See, beta 1 is momentum constant, beta 2 is RMS props constant. We mixed both in Adam. Do you see that Adam is the most powerful one? We can say theoretically, but sometimes SGD works better than all these. Okay, we need to try all these different things. There is an Adam also. I don't know that I didn't clearly saw what that is. N Adam, right? It's all improvement. Okay, when there are hyperparameters in a new optimization function, you need to understand how they work and how to play with them. Now we know that, right? If you take beta is equal to a small number, it will consider only less number of previous gradients. If you take beta is equal to a big number close to 1, it will consider more previous iterations. So accordingly you can play, but generally the default value is 0.9. At that point, that 0.9 value they'll work well. I never played with betas, right? Generally the default values worked well. Okay, any questions here?
So what is that basic correction, sir?
I'll come to that. I'll come to in batch normalization I'll come to that. Maybe I'll show code for this, maybe 5 minutes or 10 minutes, and then I'll come to that. So there is bias correction, right? This 1 by 1 minus beta, I said 10 days, right? So let us look at theoretically, and then I'll explain that. By playing with beta, we'll be able to find best relation between days and stock price, that we understood. Bias correction is a concept. Okay, this concept is used in batch normalization. Next concept I am going to explain will help exponentially weighted moving average function estimate values correctly when the iterations are at the beginning. Okay, so I told you, right, first iteration the calculation was not correct, right? V of x1 is only taking 10% of y1. But if you use this formula, right, v of xt is equal to v of xt divided by 1 minus beta power t, right? This formula divided by 1 minus beta power t. Right? V of xt is equal to this formula divided by 1 minus beta power t. If you take, even this one will also be correct. Substitute that here. Let me take a screenshot and explain. what I said is the bias correction, right? Bias correction is a concept, and I said that this formula I am changing it to divided by 1 minus beta power t. Okay. Here, what is, if you use the same formula, right? Divided by 1 minus, what is beta? 0.9 to the power of t is 1, right? I kept 1 there, right? So it's going to be 0.1 into y1 divided by 1 minus 0.9 is 0.1. You got y1, right? And the second, equation also, if divided by 1 minus 0.1 to the power of 9, 0.9 to the power of 0.9 square, 0.9 square is 0.81, right? 1 minus 0.1 and 0.81 is how much? 1 minus 0.81 is how much? Divided by 1 minus 0.81 is
0.19.
0.19. 0.19, right? Divided by 0.19 here, divided by 0.19 here, right? So 1900 divided by 19, right? My 5 by this divided by 100. 100 is how much? 19, right? So let me try to put it in red. 0.9 into 0.1 into y1 divided by 9 by 10, 1 by 10, 19 by 10, 100, 10 plus 10 by 100 into y2 divided by 19 by 100, right? Yeah, that's it. So this will cancel, this will cancel. And 19 I have taken here, right? This is 9, right? 9y1 plus 10y2 divided by 19 and divided by 19. So 10 times of y2 divided by 19, right? It's almost, if you consider y1 and y2 are kind of same, right? It's going to be 19 y2 divided by 19, right? I exaggerated a little bit. Do you see that? This is 9 by 10, 1 by 10. The 100 got cancelled, right? 10 by 100 here. So this is actually 9y1 plus 10y2, right? 9y1 divided by 19, 10y2 divided by 19. Suppose that y1 and y2 are close to each other. Then what I can say, it is 19y2 by 19, right? 19 gets cancelled and y2 you get, right? So second equation also is predicting correctly. By adding this bias correction, initial steps will get corrections well. Now the predictions of the initial steps, if you take 0.9, first 10 steps, it is not going to calculate correctly. But if you use bias correction, right, the calculation will be correct. Did you get that point? Did you get that point? Any questions there?
Yes, sir. Then when to use it and when not?
I'll explain. In a moment, I'll explain, right? I said that, initial steps, initial 10 steps, it will work fine, right? But after 10 steps, what happens? Let us see, right? After 10, generally bias correction is not going to help much. Only, if you take 0.99, right, then it's going to be 100 steps, right? That time bias correction will help, because 100 steps, the prediction is not going to be correct. This bias correction will actually make it correct. If it is 0.9, right, not use, no use. Only 10 iterations we can afford. We can afford to have some mistake there in the first 10 iterations, right? So in the 11th iteration, what will happen? Let us take 10th iteration, right? There is some v of x10 divided by what? 1 minus 0.9 to the power of 10. 0.9 to the power of 10 is how much? 0. Where is it? 0.9 x to the power of 5 and 10. Where is equal to? See that? it is 0.34. 1 minus 0.34 is, right? If you take 100, right? Let us take 0.9 x to the power of by 100. Say 0.0000 whatever, right? 1 minus whatever, this is going to be 1 only. The denominator at higher iterations, the denominator, even when you use bias correction in the higher iterations, the denominator effect is going to be reduced, right? After a certain number of iterations, right? The denominator, this new terms effect is going to be reduced. It will help you predict well or understand pattern well in the initial stages of the iterations. Okay, so that is, we will actually use it in give me 1 second. I've got a message, give me 1 second. Okay, so so that's the point. Now, Seshram, your question got answered, right? Initial iterations will help, but going forward it will not help. So generally bias correction will not use, but in batch normalization they used it. So I wanted to explain that here, because the concept I need to cover, right? So that's where I explained. Did I answer your question?
Yes, sir.
So let us look. Oh, yeah, please.
For the API, do we have an option to specify this?
Yeah, we have.
Use?
Yeah, we have. In momentum RMS prop, I think we don't have, but in batch normalization we have it. Okay, so let me activate the environment. I am just using this because it will get used to you, right? So I created a virtual environment TensorFlow. I changed it, and now I am going to open Jupyter Notebook. Oh, we have already. I think the code is already there with you. There nothing. Only simple change will be there. Yeah, momentum RMS. So I said 2 because I used to have both code, 1.4, 1.14 and 2. So at that time I had 2 versions, so I said 2, but now it is not needed. So I have taken the same data set, same data, right? Only thing is I would have changed standard scalar. I think I don't need this much, this bigger network. I think to show dropout regularization, I would have taken that bigger network. And see this Adam. No, Adam is has beta 1, beta 2, 2 parameters. Beta 1 is the parameter belonging to momentum. Beta 2 belongs to RMS prop. Right? Learning rate you already know. Right? Is it diverging? Class, okay. Converging only. Accuracy, it's converging only, but it's slow, right? I think I should take out these dropouts because network is not that complex, right? So I can take out the dropouts.
Sir, why we have used this empty flatten?
Where?
There
Here.
is a flatten node also.
Where? Okay.
Model.add.
It is not needed. Previously these guys, right? They changed it in 2.0. We had to flatten it, and there were some issues. So let us see. Let us see. I think flatten is not needed now. So in dense layer, it always takes flattened whatever only. It's not needed now. Previously, it used to expect us to flatten it and then pass it. Flattening is nothing but making it one-dimensional array, vector. Right? So evaluate. I think predict class is taken out. Right? We have to take predict and then we need to actually do whatever. Right? You do it. Okay. And then this is RMS prop. Right, RMS prop, and then I did not specify anything here, right? Default value I'm using, right? So default beta we'll see. Wait. Very interesting, right? So they kind of brought the time series concept and try to apply it onto the gradient descent. So it is just that some mathematical concept will roll around. Right? Same SVD, same these kinds will actually roll around many times. See, learning rate, RHO, momentum, epsilon, right? So the denominator epsilon, centered false, right? Centered means mean centering. Do we want to do data mean centering or not? We anyway applied standard scaling, right? No need to do mean centering. Okay, so here RHO, I don't know what it is. Discounting factor for the history. Let us look at the formula once. Give me 1 minute. So in SGD itself, right, they gave momentum, I think, see momentum, right? This momentum is the 0.9, whatever I said, right? 0.9 value. 0 means it is SGD only. Previously, we used to have a separate class for momentum. Did I use that? Yeah, SGD only. I have taken momentum is equal to clip value I need to talk about. Give me 1 second. Okay, momentum 0.1 I have said. The clip value is not there. What? I think they took out clip value. Okay. Clip value is there. Okay, I'll explain that. So momentum we can do it with SGD class only. In RMS prop momentum factor. Why did they use momentum factor? Give me 1 second. This formula. Discounting factor. I think this beta is called the discounting factor. And in this also momentum is there. I don't know why. Epsilon we know, centered we know. But in this momentum is there. I don't know why momentum. Momentum is just should be present in momentum only. But n atom. Right, there are beta 1, beta 2, epsilon, learning rate, name n atom, right, floating value. Decay rate. Okay, so atom, atom and anatom are kind of same, I think. The API changed a little bit. That's where I got confused. But you got the concept, right? You got the concept, right? Can I move on? Can I move on? I'll explain what is clip value in a moment.
Yes.
Yeah. So let me show you this. This in SGD, right? There are star keywords. Do you remember what is star keywords?
Keyword arguments.
Keyword arguments, right? Allowed to be one of the clip norm or clip value or clip norm or clip value, right? Gradient by norm. Gradients by norm means, right? So yeah, I think let me explain clip value first. Then we'll talk about clip norm. So clip value means, I said that there will be exponential. Exploding and vanishing gradients, right? In that concept, what we can do is when the weight values are exploding, right, or the gradient values are exploding, then weights will actually move in wrong direction, right? To control that, you can specify the clip value should be between -1 and +1. To say that, if you say clip value is equal to 1, somewhere here I said see, clip value is equal to 1, whatever gradients you get, it will try to bring them down to between -1 and 1. Okay, this is called as gradient clipping. Gradient clipping. We are actually trying to bind, or we are actually trying to limit the boundaries of the gradients to stick between -1 and +1. If you say 2, right, it will be between -2 and +2. Say 3, it will be between -3 and +3. Is this variable useful on a small network like this? No, never. If you are building a 100-layer network, then the clip value will help you, not to get into exploding gradients problem. Got it? Clip value, you got it? Did you get clip value?
Yeah, so it's only used in the exploding.
Yeah.
To restrict the exploding of the network.
Yeah. Right. This is actually, by clip norm means, it's by normalizing the data. I think the normalization factor that you want to use to clip the data. Clip value is straightforward compared to clip norm. Right. So you wanted to fix data between, -2 and +2 in a normal distribution, right? So you should be specifying that clip norm is equal to 2 or 3. Then it will actually adjust those weights in such a way that the ultimate weights are going to come in normalized fashion. Okay, clip value is not going to look into that. It will just try to apply some formula to bring all the values between -1 and +1. How can I do that? In min-max scalar, you can specify the range, right? In min-max scalar, we have used the standard scalar and min-max scalar to scale the data, right? So it will apply min-max scalar. When it applies min-max scalar, right, it takes all the weights and applies min-max scalar. Everything will come between -1 and +1 with the range -1 and +1. Takes minimum, maximum, subtracts minimum divided by maximum minus minimum of all the weights it found or the gradients it found. Okay, then everything will come between -1 and +1, right? That is clip value. Gradient clipping, we call this concept as. We don't want to explode the gradients, so we clip them in a range. Okay, so that is Adam, RMS prop, and momentum. Okay, so we can move on to the next concept, next optimizer, which is called as batch normalization. Okay, so this is this is the in optimization, right? This is the last concept. Okay,
Sir,
so
can you please go to the RMS prop once?
API
No, here only.
code
No.
API.
Slides.
Yeah.
Where are we actually using B1 and B2? Maybe next one, I think.
Adam.
Okay. Adam, please go there. So where actually we are using both B1 and B2 here, sir?
In this formula, right? There are two values we are using: alpha into V of dj by dw. Where we are using B1, beta 1. Mm-hmm. In S dj by dw, we are using beta 2. Right here.
Yeah. Can you please remove that highlighting?
Yeah.
Okay. Sir.
Right? Yeah. Yeah. When I highlight, right, the letters are going off.
Yes.
Yeah. Okay. So here, the next concept is batch normalization. So this thing is found by Google, guys. The basic concept they wanted to the basic problem they wanted to solve is data distributional differences. So the point here is, right, suppose that you have three different cameras, Nikon, Canon, and maybe Fuji, okay, with three different resolutions. And we were actually trying to do maybe object detection, right, vehicle detection. I asked to take pictures, and three different people actually took cameras, three cameras, and they went and took pictures and came back. All three cameras are of different pixel densities and different companies, right? Now we got the data, and I took Canon cameras. Canon came faster, so I took Canon cameras data and trained a model, right? So now I am actually trying to test the model using, Nikon's, outcome. Okay, Nikon camera's outcome I am trying to, the pictures I am trying to predict. Will the model work? Will the model work? The pixel densities are different. Will the model work?
No.
No, right? Because the data distribution is different. When I say data distribution, there is a concept. In image processing, you take histogram of image, right? Suppose that you want to identify whether the car is same or not, right? You have 100, for each car, you have maybe, five pictures of each car. Five pictures of each car you have, right? 100 cars you have, right? 500 pictures. So you try to take one car pictures and try to do histogram of it. You know histogram, right? How to do a histogram of a picture? How to do a histogram of a picture? So we pick, we took handwritten digit and we converted it to pixels, right? The pixels are nothing but numbers, right? You can actually do you take one record, one row, and then do a histogram of that data, right? 784 pixels you take, and then histogram of it, right? Can I do that? Can I?
Yes, sir. The counts of the pixel, right?
Counts of the pixels. 0, how many? No,
Yeah.
1 pixel, how many? Or maybe 0 to 10, how many? 10 to 20, how many? 20 to 30, like 254 till 254 we'll have, right? So that is called a histogram, right? For each car, you try to take histogram, right? They'll have some pattern. You understand that. Second car, understand. Third car, you understand. A new car came in, right? You try to do histogram and try to understand. So that is data distribution, right? Of the pictures, data distribution you are trying to. So if you take pictures using different cameras, the data distribution will change. Will it change? If I take a Nikon with 20 megapixel and Canon with 5 megapixel, if you take pictures and bring the photo and try to look at the data distribution, will that change? Will the data distribution change? When you do a histogram, will the bar heights change?
Yes, sir. Obviously.
Bar height change, but maybe they'll have similar pattern, but the bar heights are going to be different, right? That's the concept. That's the point you need to remember. Bar heights are different, but the pattern may be same, right? When the pattern is same and bar heights are different, if you divide the value with maximum number, you normalize the data, will both graphs come to the same place? No, the point I am trying to explain here is, suppose that you have taken Nikon's histogram and Samsung's or Canon's histogram, right? In this, right, your bars, maybe it's a 20 megapixel camera. This is a 5 megapixel camera, right? So 100, 50, that's enough. This is 10, 5, right? So the between 0 to 20, 20 to 30, 30 to 40, 40 to 50, maybe pixels only 50 are there. Here also 20, 30 pixel number it is, right? 40, 50, right? So most probably the graph may be like this. The bar may be like that. Right? Shape may be different, same, but height may be different, right? The scale may be different. If data is like this, right, what you can do, you take maximum here, divide, maximum here, divide, everything comes between 0 and 1, right? Then do a graph, both will be same. Do you remember that concept? Both graphs will be same. Do you remember that concept? Similar scale, bringing data into similar scale, right? That is normalization, okay? So we are trying to do batch normalization while training the model, while understanding the pattern. The batch normalization will try to, try to solve the distributional differences in data. Even though the data is brought from different sources, if you train a batch normalization network, it works. That is theory. In practice, it will not work. Okay, there is no guarantee. I shouldn't be saying it will not work, but there is no guarantee. Okay, but theoretically, they think it works. Okay, so here, how batch normalization network works? See, you passed x1, x2. You calculate z. What is z? What is z? What is z? Huh?
Z is the linear combination.
Linear combination. Terminology is very important, right? That's the point I was actually looking for. When in interview also you speak like that, right? They know that you are actually in this field for maybe at least 1-2 years. Okay, so in interviews, right, we know subject, but expression is also very important, right? Unfortunately, that is the case there. But in some interviews they'll give data set and ask you to work. That is better than just asking questions. Sometimes that also gets into trouble because the interviewer would have done something on the data set. He would expect you to do the same thing. So that's another problem. But ultimately, it's all luck. Okay, so all the best. So, right, so the G, right, Z is the linear combination you calculated, and then Z norm. Z norm is the normalized value of Z's. I am saying Z's. I am not going to pass one value here. I'll pass a batch of values. Suppose the 32 records are passed, you will have 32 Z's, right? You can do normalization of those 32 because you will have a mean, you will have a standard deviation of all those 32 Z's. Do you agree? Till that point, do you agree? Huh?
Sir, please come again, sir.
So I passed 32 records here. X1, X2, 32 records I passed. So I'll get 32 Z's, right?
Yeah.
Right? So here I'll get 32 Z's and here also I'll get 32 Z's. I can normalize the data. What is normalization? Z norm is standard normalization, standard scaling. Z score calculation. Z minus mu divided by square root of sigma square plus epsilon. Now variance we are calculating. Unfortunately, we may get zero variance. When will we get zero variance? When will we get
all
zero?
the data points are same.
All the data points are same. Will we get that situation? All the data points same situation? Will we? Anytime? Can we induce that? All the data points same behavior into data set? If you do bootstrapping of the data, right? For some reason you have done bootstrapping, right? Bootstrapping is what? 67% you take original data and rest of the 33% you reproduce from the 67 only, you copy paste, right? So that time you may get it. So all Z's are same, then your the variance may become 0, and to avoid divide by 0, we are adding epsilon here. Again, it is also 10 to the power minus 8 or something. And you calculate normalized Z value, and then you calculate Z tilde, and then you apply the activation function. Here I have taken sigmoid, but you can take ReLU also. What is Z tilde? You will take another hyperparameter, gamma and beta. These gamma and betas are randomly chosen initially, and they'll get adjusted. Along with W's, there will be gamma and beta additionally got added to the Z's, right? So you calculate Z norm, right? All the normalized Z's, and then for all the normalized Z, you calculate Z tilde. Using all the normalized Z's, you calculate Z tilde. So we are normalizing data, right, to avoid data distributional differences, and then trying to understand pattern. We try to understand a little pattern here, then normalized the the linear combinations, and then we are trying to understand pattern, understand the non-linear pattern on top of the Z tilde. Right? Z tilde, there are these hyperparameters also learned over a period of time. So that is batch normalization. Basically, we are doing normalization of data in each iteration. In each layer, the normalization is happening. That way, at some number of layers, right, the data distributional differences will go off. You may take pictures from your camera, or you may take pictures from internet, train your model, and you take pictures from your camera and then try to use it for in production, or maybe for testing. The model should work. That is batch normalization. Okay. So that's the concept. I think this is useful in our speed detection system. We were actually struggling with this. Whenever we get a new camera, we were taking a couple of videos and then collecting data and training the model again, retraining the model again. Yeah, but I think if you apply batch normalization, right, the retraining effort will reduce maybe. Maybe I have to experiment and see. Got it? Theoretically, you understood what it is? I can move on, right?
Yes, sir. One second, sir. So here we took the example of, let's say we are passing 32 records. So after normalization also we'll get the 32 Zs, right? But those are all in the same scalar.
Same normalized, similar scale. Now we are calculating Z score, right? Z score will not guarantee between a range, but it will shrink the range. Thinking?
Yeah. And one more thing is like the example we took, like the different cameras has different pixel density. That means the input features are varying, right?
We will anyway try to bring that to same size, right? So maybe by applying dimensionality reduction kind of technique, right? We do some normalize, some technique and bring them down to same pixels. Or we take, there are tools, there are actually functions in scikit-learn and TensorFlow, which will let you know the dimensionality you want to extract. Whichever picture you get, you want to say 216 by 216 by 3. It will give you only that many pixels. So input dimensionality is going to be same.
Okay. So even after changing that, let's say we got pictures of different dimensions and we applied dimensionality reduction using PCA. Even after that, do we need to apply this batch normalization?
PCA, yes and no. PCA may damage data also, right? PCA, right? If the correlation is the factor which is dominating the feature you want to identify or the object you want to identify, then model will work well. But if the correlation is not the factor, right? It will damage the picture and you may not identify anything there, whether you apply batch or not.
Yeah, I said PCA because maybe let's say some other dimensionality reduction.
Yeah,
we need to apply this.
If you are if you take machine learning, right, it is all unsupervised dimensional direction. We'll see CNN where we'll do supervised dimensional direction. There, there it actually works. Supervised dimensional direction and batch normalization will work.
Okay.
In CNN we see that supervised dimensional direction. Even in DNN also it is there, but I'll highlight that part there. Even in DNN also the dimensional direction is there. See this here? On a network, right? You take 128, you pass some input, you take 128, you make it 64, you make it 32. Right? What are you doing here? We are actually reducing dimensionality. With each layer, the dimensionality is reducing, but while looking at the y variable and the cost function, it is reducing the dimensionality. Right? In deep learning, you can do supervised dimensional reduction. Got the concept?
Yeah, the dimensions of the layers are decreasing, but the input features are not decreasing, right?
Input only, right? You pass 784 here, it reduces to 128, it reduces to 64, it reduces to 32, while reducing your understanding pattern also parallelly. In a machine learning algorithm, right? You are taking 784 and directly calculating probability. Here we are reducing, and then understanding the probability. Got it?
Yeah.
You can take the, once the model is working good, right? You can take this layer's outcome and represent your original picture. That is one concept where we use in face detection. Okay, you take your, all the faces in your office, try to build a neural network that understands the pattern in a reduced dimensional fashion. You take a picture, it may be 5,000 pixels. You try to build a network that actually understands each picture in 32 pixels. You convert all your 1,000 people data into 32 pixels and put it into database. A new photo came in today, right? Somebody stood in front of the camera. You take picture, reduce it to 32, and then check it with your database. Euclidean distance you calculate. The number of calculations will reduce that way. When network is proficient, efficient in understanding the pattern and making the predictions correct, you can take, the nth layer's outcome as a representation of your picture or your input. In face detection, we'll talk about this again. Got it?
But if an image is represented in these less number of pixels, will that identification be accurate?
Yeah, mathematically it will be accurate, but pictorially you want to reproduce the picture, you will not be able to do that.
Yeah.
Original picture you will not be able to reproduce, but mathematically it will be correct. It is like human understanding, right? You may see Taj Mahal, or maybe Padmanabha Swami temple in wherever, right? So you can articulate it. You may have stayed there for 3 days or 4 days, maybe Tirupati, right? But you come back and say in one word or two words, right? That actually gives the other person a little perspective. Like that it is. So when you take this deep learning, right? So that's like that. The dimensional reduction in deep learning, and it is reliable. It is reliable, right? So in PCA, you are blindfolded. You don't know whichever data you give, you go in the same direction. Correlation extraction, right? But here it is not like that. It actually shows you direction. The cost function actually shows you direction while reducing dimensionality. These are all simple concepts, but when the people write books, right, they made it too heavy. Okay, when we understand the face detection, right, it becomes easy. I actually already explained that, gist of it. Okay, so any other questions? Sorry, any other questions? Okay, so batch normalization is this one, right? There is some theory in this. Let me cover that and show you the code example. Normalizing input for nodes in deeper layers will make it easy for node to find better weights and making convergence faster. Covariate shift. There is a concept called as covariate shift. Right? When input data distribution changes, the algorithm need to be retrained. The example I took, right? For speed detection, whenever we change the camera, we are actually retraining the model. There, the batch normalization is very useful. But currently, we are kind of pre-production mode, and we still need to get some machines and all that. So we don't have necessary hardware there. That's where we are hesitating to do these changes. When we get them right, we'll do that. Okay, batch normalization reduces the amount of oscillation in distribution. The other, in other words, the normalization tries all inputs in all nodes with same data distribution between mean 0 and variance 1. Why mean 0 variance 1? When you actually calculate z-score, right? The z-score values of the original data are going to have 0 mean and 1 standard deviation. Z-score values, z-score values of the original data, z-score values of the original data are going to be in 0 mean and 1 standard deviation. Okay, that's the point here. Right? And then if you see this here, if you take 32 records batch, the mean and standard deviation is going to be different. When you take 64 records batch, the mean and standard deviation are going to be different. When you take 128 record batch, the mean and standard deviation is going to be different. Do you agree with that statement? The batch size determines the mean and standard deviations quality. Do you agree with that statement?
Yes.
Right. So what we are doing while calculating this z-norm, each batch we are taking that batch's mean and that batch's standard deviation. Right. That may actually oscillate data a lot. Right. But instead of taking like that, right, you take mean as a cumulative mean, right? You first batch you got some mean, second batch you got another mean, third batch you got another mean. While doing third batch, you take mean of all these three means. While doing fourth batch, you take mean of all four means. Like that, standard deviation also, right? So like that also we can do. Okay, so that concept somewhere here. So no need of adding bias term B. That's one concept I need to explain. When we apply batch normalization mini batch gradient, mu and sigma are calculated on data available in mini batches. When mini batch size is small, there will be noise calculated. When batch size is mini batch size is small, mu and sigma are not going to be universally accepted. They're going to be oscillating a little bit. This oscillation actually adds a little bit of regularization. That's an unexpected regularization. When I say regularization, it tries to reduce overfitting. In a way, model works a little less accurate, right? Model will be a little biased. When you apply batch normalization, model will be a little biased, and it may actually reduce overfitting because of this batch sizes. Generally, when you do batch normalization, it is better to take bigger batches. And there is one more concept called as taking average of the previous batches, means and standard deviation, and using it. Both way, right? It may actually work better, make the model better. The other concept is no need to add bias term here. If you add bias term, what happens? See this here. Z is calculated, and then Z's normalization is being done, right? Let me try to show that. No need to add bias term. Even if you add bias term, that gets nullified. How? I'm going to show. In batch normalization. In batch normalization, even if you add bias term, it is going to get vanished. Right? See that here. Right? Suppose that you passed B also. Right? So Z is going to be what? X1, no, W1 X1 plus W2 X2 plus B. Okay. Maybe I'll put one here. That is first record. Okay, so I am and the second record, right, W1 X1 2 plus W2 X2 2 plus B, right? So like that, I have calculated Z values. This is Z1, this is Z2, like that. Now what I am doing, I am calculating mean here, right? When I calculate mean, what I will do, I will sum this and this, right, and all divided by n, right? Suppose that there are 32 records I passed, okay, right? Then what will happen, right? W1 X1 plus W2 X1 X11 plus W1 X2. I did not took B intentionally. Okay, 2 plus W. I think I should take another color. Is this visible? Is this distinctly visible? No, right? Let me take another color. So now I am calculating mean, right? Mu. How will I calculate? W1 X1 plus W2 X2 plus W1 X1 2 plus W2 X2 2 plus and so on, right? 32 ones plus 32B. Do you agree? 32 into B. Do you agree? In every Z there is a B, right? There are 32 Z's, 32 Z's, right? So there will be 32B divided by 32. Right? This is mean, right? Do you agree? Any questions here?
So are you assuming like the B will be, the bias term will be same for each record?
Yeah, bias term will be same, right? One, always one it is. I think I should x0, sorry.
X0, okay.
X0, but for a batch, B is going to be same, right? B is the weight. That's a good question. X0 is 1, right? For a batch, B is going to be same, right? For a batch, all these weights are same. For a 32 record batch, all these weights are same. Next iteration, they'll get adjusted. Again, they're going to be same for that batch. Agreed?
For a batch, for one neuron, all the weights will be same, right?
Yeah.
Okay, and B is also same. So if it goes to the other neuron,
Then B is going to change.
Weights
Maybe
will also
B1.
be changed, right?
They'll change.
No, not there. Here, in the same layer, the second neuron in the same
This
layer.
one, yeah. This one B will be same here also. The same B will go here also. But weights may be, the green weights may be different, the yellow weights may be different, but B is going to be same.
Okay. So the intercept term is same for all the neurons, for all the records in the batch.
Yes.
Okay. Please.
Yeah. So here, this 32B, right? 32 will get cancelled, and in mu you will have B only. Now, when you calculate Z norm of first record, what is that? W1 x1 1 plus W2 x2 1 plus B minus B, right? This Z minus mu, right? Z minus mu is like minus of this whole whatever, right? Minus B, right? Plus B minus B will get cancelled, divided by square root of sigma square plus epsilon. So bias term, even if you add, it is getting cancelled when you actually do normalization. So no need to add bias term. But here it gets added, the bias term, the beta is kind of a bias term that gets added, gamma and beta thing. But your bias term is not needed. These values will be randomly chosen while network is getting trained. Got it? In batch normalization, bias term is not needed. Okay. Got it? Can I move on? Okay, let me show you the code. Simple. Code is nothing. You understand the concept? Code is nothing. The API is there and it has got everything there. See this? You do a dense layer, pass it to the batch norm, then apply ReLU. Dense layer, batch norm, ReLU. Why? Look at the diagram. Dense layer, right? Batch norm, right? And ReLU. Dense layer will calculate linear combination. Without any activation, I have taken that. See this in the code? No activation. Okay. I think this is old TensorFlow, the Keras code, I think this is. But that's okay. That's okay. I think I took more model, not the series, sequential thing. So, I took dense layer without activation and batch normalized and then applied ReLU. Dense, batch normalize, ReLU. Dense, batch normalize, ReLU. Like that it is. Okay. So I'll upload this code. You experiment with it and you will know. So that's it for today. And any questions you can ask. And I have a question. Are you guys getting it? Are you guys getting it? I don't see all of you talking, but I know that you are getting it, but I'm just checking.
Yes, sir, we are getting it, sir.
Okay. So you need to play with the code. Definitely you need to play with the code, because in a week I'll give you one exercise that needs all this knowledge, and it may take 10-15 days for you to actually kind of do something useful. Okay. If you are able to do that exercise, right, you'll get full control over CNN, DN, and basically all neural networks. Okay.